For decades, we had a story, a grand cosmic narrative we were pretty confident was true. It was the story of the beginning, of how the first lights in the universe flickered on. We called it the cosmic dawn. After the unimaginable fury of the Big Bang and a long period of absolute darkness, the general consensus was that we'd see a slow, gentle sunrise. A few faint, messy, infant galaxies gradually blinking into existence, like tiny embers scattered in an infinite night. This was the orthodox view, the bedrock of modern cosmology. That's the story we were so sure the James Webb Space Telescope would finally confirm, showing us the faint, larval stages of cosmic evolution. But when it finally opened its golden eyes and peered back across 13.5 billion years to the dawn of time, it didn't just find embers. It found a furnace. It saw a universe already blazing with activity. It found galaxies that were far brighter, far more massive, and far more developed than they had any right to be so early. It was like expecting to see a few scattered huts and instead finding a bustling metropolis, complete with skyscrapers, already built and shining in the twilight of creation. This discovery didn't just add a new chapter to our story. It sent astronomers scrambling for better explanations. It has created a profound and thrilling tension in the field, forcing us to ask a tough but exciting question. Is our understanding of how the universe grew up missing a key piece of the puzzle? What the James Webb Telescope is revealing is nothing short of a paradigm shift. The images it sends back aren't just beautiful postcards from the edge of time, they're pieces of evidence from a cosmic crime scene. The victim, our neat and tidy theory of galaxy formation. The suspect, a universe that seems to have a secret history, one that unfolded far faster and more furiously than we ever dared to imagine. We're now faced with a universe of impossible objects. Galaxies with the mass of hundreds of millions of suns, shining with the light of 1 trillion stars, existing when the universe was only 2 or 3% of its current age. This shouldn't be easy. It's like finding a fully grown adult in a world that's only been around for a week. It creates real tension with the fundamental rules of growth that we thought we understood. Every new deep field image from Webb seems to uncover another one of these anomalies, another defiant galaxy that spits in the face of our predictions. The puzzle isn't just that we've found 1 or 2 strange objects, it's that the entire cosmic nursery seems to be filled with them. The trickle of strange data has turned into a torrent, and astronomers are scrambling to make sense of it all. This isn't a minor adjustment. This is a major rethink. To understand why these discoveries are so earth-shattering, you first have to understand the blueprint we were working from. It's called the Lambda Cold Dark Matter Model, or Lambda CDM for short. For decades, Lambda CDM has been the standard model of cosmology. It's been fantastically successful, accurately describing everything from the faint afterglow of the Big Bang to the large-scale web of galaxies we see today. Think of it as the master recipe for building a cosmos. The recipe has 2 main mystery ingredients: lambda, representing dark energy, the enigmatic force pushing the universe apart at an accelerating rate, and cold dark matter, an invisible form of matter that provides the gravitational scaffolding for everything we can see. According to this model, the story of the first galaxies should be one of slow, bottom-up construction. Imagine the aftermath of the Big Bang. The universe is a vast, dark, and mostly uniform soup of hydrogen and helium gas, embedded within an invisible web of cold dark matter. This dark matter, being much more abundant than normal matter, is the first to start clumping together under its own gravity. It forms small, dense pockets called halos. These halos are the cosmic seeds. Normal matter, the hydrogen and helium gas, is then slowly drawn into these dark matter nurseries. But this process is supposed to be gradual and inefficient. Gas needs to cool down enough to collapse and ignite the first stars. These first galaxies, the pioneers of the cosmic dawn, were expected to be mostly small, faint, and disorganized, what astronomers call protogalaxies. Over billions of years, these small fragments would collide and merge, gradually building up into the larger, more structured galaxies we see today, like our own Milky Way. The key words here are slow and gradual. Lambda CDM predicted a mostly gentle, protracted dawn, not a sudden explosion of light. And this is where the crime scene evidence comes in. JWST is the detective that has arrived on the scene and found that the story doesn't quite match the facts. Take, for example, a galaxy named JWST 14-0. It's a name that might not roll off the tongue, but it will be written in astronomy textbooks for decades to come. JWST confirmed we are seeing this galaxy as it was less than 300 million years after the Big Bang. The universe was a mere infant, only about 2% of its current 13.8 billion year age. According to our Lambda CDM blueprint, at this point in cosmic history, we should be finding, at best, a few dim protogalaxies, just beginning to assemble. But JWST 14-0 is anything but dim. It is shockingly luminous and sprawling, with estimates suggesting it's already about 1/600 light-years across. Its brightness implies it's packed with hundreds of millions of suns worth of stars. This galaxy didn't just form, it appears to have matured at a breakneck pace that our models struggle to replicate. And it's not alone. Astronomers are systematically finding that the early universe was teeming with these unexpectedly large and bright galaxies, in greater numbers than many pre-JWST models anticipated. The problem is one of timing and efficiency. To build a galaxy as massive as JWST 14-0 so quickly, the entire process described by Lambda CDM would have had to happen in fast forward. The dark matter halos must have grown faster. The gas must have cooled and collapsed into stars far more efficiently. The whole assembly line of galaxy formation must have been running at a speed our master recipe deemed unlikely. It's not just that the universe was building things, it was building them bigger, better, and faster than we ever thought possible. So, we found some galaxies that are too big and too bright. Why is this attention? Why can't scientists just tweak their models and move on? The answer is that this isn't about a minor error in calculation. This is a direct challenge to the physics of galaxy formation within our cosmic story. The Lambda CDM model isn't just a casual theory, it's the culmination of decades of observation and theoretical work. When you find evidence that creates such a profound tension, it's not like finding a typo in a book. It's like finding out the book might need a new, heavily revised chapter. The stakes are enormous. If the physics of galaxy formation within Lambda CDM are flawed for the early universe, what else might need revising? While most astronomers don't think this overturns our understanding of dark matter or dark energy, it does force a major rethink of how the first structures came to be. To challenge predictions at the cosmic dawn is to pull a thread that could lead to a much richer, more complex understanding of cosmology. This is why astronomers are using words like tension, puzzling, and challenge. They aren't being hyperbolic. They are expressing the genuine shock of a detective who finds evidence that defies expectations. It's a moment of both profound uncertainty and incredible opportunity. Science doesn't advance when theories are just confirmed, it leaps forward when they are challenged, and JWST may have just taken a sledgehammer to some of our most detailed models of galaxy formation. The problem runs even deeper than just brightness. It's also about chemical maturity. In the beginning, the universe was made of only the simplest elements: hydrogen, helium, and a tiny trace of lithium. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in rocks, had to be forged in the nuclear furnaces of stars and then scattered through space when those stars died. This process of chemical enrichment takes time. You need generations of stars to live and die to build up a significant reservoir of these heavier elements, which astronomers collectively call metals. Our models predicted that the very first galaxies should be chemically pristine, made almost entirely of hydrogen and helium. But in a stunning discovery, astronomers using the ALMA observatory targeted JWST 14-0 and detected the signature of oxygen. Finding significant amounts of oxygen in a galaxy less than 300 million years after the Big Bang is like finding a multi-generational family tree in a town that was only founded yesterday. It implies that at least one generation of massive stars had already formed, lived its entire life, exploded as a supernova, and seeded the surrounding gas with the heavy elements it created. All of this happened in a startlingly short amount of time. The galaxy isn't just surprisingly big, it's surprisingly old in its composition, far more chemically evolved than it seemed it had any right to be. So the puzzle is multifaceted. The galaxies are too big, they are too bright, and some are too chemically mature. It's a trifecta of surprises that has forced the entire astronomical community back to the drawing board. The old story needs a major revision. Now, the thrilling, frantic search for a new one has begun, and in this cosmic mystery, there are several prime suspects. The first and most tantalizing possibility is that these early galaxies aren't quite what they seem. What if they aren't actually as massive as their brightness suggests? What if there's something else inside them? Something small, powerful, and incredibly bright, that is lighting them up from within and creating the illusion of a massive stellar population. The prime suspect for this hidden engine is the most powerful object in the universe, a supermassive black hole. We tend to think of black holes as objects that consume light, but the region around a black hole can be the complete opposite. When a supermassive black hole at a galaxy's center actively feeds on surrounding gas and dust, it forms an active galactic nucleus, or AN. As matter spirals into the black hole, it gets compressed and heated to unimaginable temperatures, causing it to glow with an intensity that can outshine all the stars in the host galaxy combined. So, the theory goes like this. Perhaps these impossible early galaxies are actually much smaller, less massive collections of stars, more in line with what Lambda CDM would predict. But, lurking at their centers are ravenous, rapidly growing supermassive black holes that are flooding their surroundings with so much extra light that they appear to be galactic giants. The galaxy isn't overly massive, it's just being photobombed by its own central monster. JWST has found compelling, though debated, evidence to support this idea in a strange class of objects dubbed little red dots, or LRD. These are compact, intensely red sources common in the early universe, whose exact nature is still a mystery. When astronomers look closely at some of these LRDs, they find the telltale signs of active, accreting supermassive black holes. The light from these objects appears contaminated by the fierce glare of matter, being torn apart at the edge of an event horizon. A galaxy named Canucks LRDZ 8.6, seen just 570 million years after the Big Bang, provides a perfect case study. It hosts an active supermassive black hole that appears overmassive compared to the stellar mass of its host galaxy. This challenges the old story of coevolution, where we believed galaxies grew first, and their central black holes grew along with them. This evidence suggests that in the early universe, the black holes may have come first, growing at a furious pace, and perhaps even triggering star formation in the galaxy around them. Another piece of evidence comes from a galaxy nicknamed Virgil. To most of JWST instruments, Virgil looked like a normal, distant star-forming galaxy. But when astronomers used the mid-infrared instrument, or MIRI, to look at it, they saw through the dust and found a secret. Hidden at its core was a rapidly growing, overmassive black hole. Without MIRI ability to see the heat glow from the obscuring dust, we would have completely misjudged the galaxy's nature. This implies there could be a hidden population of these dust-enshrouded black holes in the early universe, masquerading as normal galaxies. But this solution, like all good plot twists, only deepens the mystery. If the brightness of early galaxies is explained by early supermassive black holes, we now face an even harder question. How did the universe make supermassive black holes so quickly? A standard black hole forms from the collapse of a single massive star. These stellar mass black holes are maybe a few dozen times the mass of our Sun. To grow one of these into a supermassive black hole 1,000,000 or 1,000,000,000 times the Sun's mass should take an immense amount of time. While models involving super Eddington accretion, feeding faster than the theoretical limit, or slightly heavier initial seeds make it possible, explaining how common these behemoths seem to be is the real challenge. This has led to radical new ideas. Perhaps the very first stars weren't like normal stars at all. Some theories propose the existence of monster stars, or even dark stars powered not by nuclear fusion, but by dark matter annihilation. These theoretical behemoths could have been millions of times the mass of our Sun. When they finally collapsed, they could have formed a massive black hole seed, weighing tens of thousands of solar masses. This would give the universe a tremendous head start. Some astronomers even speculate that some of the little red dots JWST is seeing aren't galaxies at all, but these hypothetical monster stars themselves. So, suspect number 1, the hidden black hole, is a compelling explanation for the brightness of some of these galaxies. But it forces us to reimagine the origin of the universe's largest monsters, suggesting a violent top-down formation process that is a universe away from our old, gentle, bottom-up story. But what if the galaxies really are as big as they look? What if there's no trick, no hidden engine? What if the problem isn't that something is making them look brighter, but that they are genuinely burning with the light of an enormous number of stars? This leads us to our second major suspect. Star formation in the early universe was not just efficient, it was hyper-efficient, working in a constant state of overdrive. This theory doesn't throw out the fundamental lambda CDM model. Instead, it argues that our understanding of the physics of star formation was incomplete. The conditions in those first dark matter halos were simply perfect for turning gas into stars at a shocking rate. Imagine a modern galaxy like our Milky Way. It's a relatively calm, orderly place. It produces, on average, about one new sun's worth of stars per year. It's a steady, sustainable rate. But what JWST is finding in some early galaxies are not calm factories, they are raging furnaces. Some analyses of objects like the protocluster SPT 234956 suggest member galaxies are forming stars hundreds or even thousands of times faster than the Milky Way. This intense activity can explain both the brightness of the galaxies and the rapid chemical enrichment. If you are forming stars, especially massive ones, at such a high rate, they will also die quickly and violently, spewing their freshly forged heavy elements into the surrounding gas. An overdrive factory doesn't just produce a lot of product, it also produces a lot of exhaust. So why would star formation be so much more efficient back then? The answer may lie in the raw materials. The early universe was much, much denser. Everything was closer together. Galaxies were constantly being bombarded by streams of cold gas flowing along the filaments of the cosmic web, a direct and potent fuel line for star formation. Mergers were also far more common. In the chaotic environment of the early cosmos, small galaxies were constantly crashing into each other. These mergers would trigger violent gravitational instabilities, compressing vast clouds of gas and igniting bursts of star formation that would make the rates in modern galaxies look pathetic. JWST is giving us a direct look at this chaos. Instead of majestic spiral disks, many early galaxies are messy, turbulent, clumpy train wrecks, puffed up by the energy of constant star formation and violent mergers. This overdrive factory hypothesis is attractive because it keeps the fundamental lambda CDM framework intact. It just suggests that our simulations of the physics of star formation, the complex interplay of gas dynamics, cooling, and feedback, were incomplete. We may have underestimated the universe's youthful exuberance. However, it's not a perfect solution. Even with hyper-efficient star formation, some of the most extreme objects seen by JWST push the limits of how much gas can be converted into stars in the available time. Some early interpretations suggested the required efficiency would have to be uncomfortably, perhaps even physically implausibly, high. While more recent modeling has eased this tension, it remains a point of debate. While suspect number 2 explains a lot of the evidence for some of the biggest offenders on JWST most wanted list, it still feels like part of the story might be missing. This leads us to our third, and perhaps most radical, suspect. We've investigated a hidden culprit making galaxies look bright, and we've investigated a factory working in overdrive. But what if the problem isn't the lighting or the production speed? What if the issue lies with the products themselves? What if the first stars were fundamentally different from the stars we see today? This is suspect number 3. The universe was using a different recipe. When astronomers talk about the population of stars in a galaxy, they refer to something called the initial mass function, or IMF. The IMF is a statistical recipe describing the distribution of stellar masses. In a typical modern galaxy, the IMF is bottom-heavy. For every one massive, brilliant star that is born, the galaxy produces hundreds of smaller, dimmer stars like our Sun. For decades, many have assumed this recipe was more or less universal. But what if that assumption is wrong? What if, in the pristine, metal-free environment of the early universe, the recipe was top-heavy? A top-heavy IMF would mean that the early universe overwhelmingly produced massive stars. These stars are incredibly rare today, but they are disproportionately important. A single massive star can be millions of times brighter than our Sun. They also live fast and die young, burning through their fuel in just a few million years. If the first galaxies were built with a top-heavy IMF, it would help solve multiple problems at once. First, it would naturally explain why they are so incredibly luminous. A galaxy packed with these stellar titans would shine with a fierce light, far brighter than a galaxy of the same mass, built with a normal IMF. Second, it would explain the rapid chemical enrichment. Because these massive stars die so quickly, they would flood their host galaxies with heavy elements like oxygen on an extremely short timescale, explaining the chemical maturity seen in some early galaxies. The physics behind this idea is compelling. Stars form when gas clouds collapse. In modern metal-rich galaxies, these metals act as efficient coolants, allowing clouds to fragment into many small clumps, which form lots of small stars. But in the early universe, the gas was metal-free and couldn't cool as efficiently. Theoretical models suggest that without these metals, the collapsing gas clouds would not have fragmented as much, instead forming single, gigantic stars. This theory also connects beautifully back to suspect number 1. If the early universe was churning out these monster stars, it would provide the perfect pathway to creating the massive black hole seeds needed to explain the early AGN population. This idea is radical because it challenges a long-held assumption of universality in astrophysics. It suggests that the rules of starbirth itself have evolved over cosmic time. The first chapter of the universe may have been a brief but spectacular age of monsters. So now, we have 3 competing suspects. Are the impossible galaxies an illusion created by hidden black holes? Are they the product of hyper-efficient star factories? Or are they built from a different recipe of brilliant, top-heavy stars? The truth may very well be a combination of all 3. The crime scene is complex, and it's likely there wasn't just one culprit, but a conspiracy. As if the mystery of these impossible galaxies wasn't enough, JWST is showing us that the puzzle runs even deeper. The problem isn't just with individual objects, it's with the entire cosmic ecosystem. The universe didn't just build individual skyscrapers ahead of schedule, it may have built entire cities, all in a fraction of the time our models suggested it should take. One of the most profound discoveries is about the large-scale structure of the universe. According to Lambda CDM, galaxies form within long filaments of dark matter and then, over billions of years, slide along them towards the intersections, where they gather into massive galaxy clusters. This process should be exceptionally slow. Forming a mature cluster should take the better part of cosmic history. But JWST is finding protoclusters, the seeds of these cosmic cities, that are already well established at shockingly early times. Astronomers have found a protocluster named A 2744Z 7P90D that existed only 650 million years after the Big Bang, already containing a dense grouping of young galaxies. Even more dramatically, observations of a protocluster called SPT 234956 have revealed that the gas between its galaxies was incredibly hot, with one study suggesting it was at least 5 times hotter than models predicted for such an early epoch. The gas was at a temperature indicating that something had injected a colossal amount of energy into the system. What could do that? The two prime suspects are, once again, furious star formation and supermassive black holes. The combined energy from thousands of supernova, or the powerful jets and winds blasting out from active black holes, could heat the surrounding gas to these extreme temperatures. What this tells us is that feedback, whereby stars and black holes influence their environment, was already operating at full force when the universe was less than 1 billion years old, and was perhaps far more powerful than we imagined. This discovery of early, energetic clusters exacerbates the tension. Now, our models don't just have to explain how to build a single massive galaxy quickly. They also have to explain how to assemble dozens of them into a dense, interacting environment and then have them inject enough energy to heat a 1,000,000 light-year-wide region of space, all within the first few percent of the universe's lifetime. The mystery deepens with every new data release. We are not just finding that our timeline might be off. We are finding that the entire environment of the early universe was more violent, more energetic, and more complex than our tidy models had led us to believe. The gentle cosmic sunrise is dead. It has been replaced by a picture of a chaotic, ferocious, and incredibly rapid period of creation, a cosmic crucible where the rules of growth were extreme and the universe was in a hurry to build its first great structures. We stand at a remarkable moment in the history of science. The James Webb Space Telescope was built to answer our questions about the early universe, but instead, it has thrown our most detailed assumptions into question. The story we thought we knew, of a slow, gradual creation, has been challenged by a flood of evidence pointing to a much more dramatic and accelerated history. We have looked into the deepest, oldest parts of the cosmos and found a universe filled with puzzling objects, galaxies too bright, too massive, and too mature. Black holes that seem too large to have grown so fast, and entire galaxy clusters assembling and heating up billions of years ahead of schedule. We are faced with a cosmic tension, a puzzle with multiple compelling suspects but no simple solution. Is the answer in hidden, supermassive black holes that lit up their host galaxies from within, forcing us to rewrite the story of how the universe's monsters are born? Is it that the star-forming factories of the early universe were simply working in a state of hyper-efficient overdrive? Or is it something more fundamental, that the very recipe for stars was different at the dawn of time, favoring the birth of short-lived, brilliant giants? The truth is, we don't know yet, and that is the most exciting part. The tension JWST has created isn't a sign of failure, It's the very definition of scientific progress. Every great leap in our understanding has begun with an observation that made no sense. The universe isn't broken, our models are incomplete. And now, we have the incredible privilege of trying to build new ones. The data continue to pour in. With every new deep field, JWST adds another clue to the mystery. Astronomers around the world are the detectives on the biggest case in history, sifting through the evidence from the dawn of time. What we are witnessing is not the end of a story, but the explosive beginning of a new one. The universe, it turns out, is far more creative, more chaotic, and more magnificent than we ever dared to imagine. And its greatest secrets are finally, after 13.5 billion years, being brought into the light. We're living in a golden age of cosmic discovery, and the story is being rewritten in real time. What do you think is the most compelling explanation for these impossible galaxies? Are you on Team Hidden Black Hole, Team Overdrive Factory, or Team Different Recipe? Let us know your theory in the comments below. And if you want to stay on the front lines of this incredible scientific revolution, make sure to like and subscribe for more updates from the edge of space and time. The universe is full of mysteries, and we're just getting started.